In this video, we're going to walk through the actual code of a linked implementation of a binary tree. So we've talked a little bit about the heap form array and that array-based implementation, but let's now look at a linked implementation, which is more common for a tree setup. So we're going to review the files provided in the textbook, and there are a lot of them. So we're just going to kind of go through them, and we're going to focus again first just on binary tree. So there's a couple interfaces that are used. There's the tree interface, and the idea here is that any kind of a tree would provide the functionality of getting the root, getting the height, getting how many nodes are in the tree, determining whether the tree is empty, and clearing out the tree. Then there is binary tree interface, which extends tree interface. So it has all of these methods, plus it adds a method to set the root data and a method to set the tree. Okay, so this is an interface to represent a binary tree. There is the tree iterator interface, and this represents the functionality of obtaining an iterator of each of the different kinds: pre-order, post-order, in-order, and level order. So if a class implements this interface, they have to provide that functionality. So the binary tree interface actually extends both from tree interface and from tree iterator interface, so it inherits all of those methods. All that means is that any class that implements binary tree interface is going to have to implement all of those methods. But don't worry too much about the interface descriptions. Those aren't as important as just actually getting into the code and looking at what's really going on. So let's take a look at the BinaryNode class. That's where we will start. So this is a class to represent a binary node. The instance data are the data itself. So this is a generic class, meaning it can hold data of any type. And the instance data is an object of that type, so type T, call it data. And then we have two binary node instance data variables, left child and right child. So this is our classic kind of node, binary node, and it has two children. So there's three different ways that we can create a binary node. We can use the default constructor, which just creates the binary node with no data in it. What the line this parentheses null does is it calls the one parameter binary node constructor, which is this one here. So in this constructor, we're creating a binary node by specifying the data that should go in the root, but not having any subtrees. So it would just be a one node binary tree. So for that, we invoke the 1, 2, 3 parameter constructor, which is this one here. So the third constructor is you specify the data that should go in the root and the left child node and the right child node. So you basically just create the node with all three parts. And I apologize, I spoke a moment ago when I said binary tree. I should have said binary node. We're talking about binary nodes here. So those are the three ways we can set up a binary node: by specifying nothing, which just creates a node that is null; by creating a node with data but no left and right child are null; or by creating a node with data, a left child, and a right child. We just have some getters and setters to get the data, to set the data, get the left child, set the left child. We have a Boolean, does it have a left child? So that just returns whether or not the left child is null. And then get right child, set right child, and has a right child, so whether or not the right child is null. We have a method is a leaf, which just returns whether it's a leaf. And if both the left child and the right child are null, then it's a leaf. Otherwise, it's not. If either one of those right child or left child is not null, if it has a left child, a right child, or both, it's not a leaf. Then we have a method called getNumberOfNodes, and what this does, this is just meant to count up the number of nodes that are located in the subtree that's rooted at this particular node. So if the node we're looking at now is the root of a tree or the root of some subtree, how many nodes are there in that node and everything below it? So for example, using the tree that we were just looking at, the number of nodes in the whole tree is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we were to ask for the number of nodes invoke that on the one node, we would get 1, 2, 3, 4, 5, 6. So it's the number of nodes starting at that, whatever you're specifying as the current node, and then everything below it in the subtree. So to calculate that, we have to calculate recursively, right? So trees are sort of a natural way to use recursion because they are a recursive data structure, right? Because a binary node is defined in terms of binary nodes, left and right child, right? So the data structure itself is recursive. So a lot of the methods that we're going to see will also be recursive. Now, sometimes we're going to see recursion in a little bit of a different way, where we're invoking the same method but on a different node rather than the current node. That'll be a really common thing we'll see in these classes. So if we want to find out the number of nodes, what we can do is we can say, well, as long as left child isn't null, so as long as I've got a left child, let's just ask the left child how many nodes it has. And as long as the right child isn't null, let's just ask the right child how many nodes it has. And then whatever answers come back from that, I'm going to add 1 onto it to represent me, the current node. And the total number of nodes will be 1 plus that number in the left plus that number in the right. So this is sort of a classic setup of recursion in binary trees. So for example, again here, if we ask 4, well, what's the number of nodes in the tree rooted at 4? We'd say, well, I don't know. But if I could figure out the number of nodes rooted at 1, then I'd know my answer. Okay, well, how many nodes are rooted at 1? Well, I don't know. But if I could figure out the number of nodes in the 2 subtrees, then I'd have my answer. So how many nodes are rooted at 7? Well, I don't know. But if I could figure out the number, again, starting in the left subtree, I'd know my answer. Well, how many nodes are in 6? Well, 6 is a leaf. Both left and right are null. So it's going to fail these 2 conditionals, and it's just going to return 1. So the 6 will return 1, and then the 7 will say, okay, I need another piece of information. I need the number in my right tree, my right subtree. We go down to the 11, and 11 is a leaf, doesn't have any subtrees or subchildren. So we say, okay, the height here is 1. So now the 7 says, okay, I got a 1 from the 6 and a 1 from the 11, and I'm going to add on 1 for myself. So that means the number of nodes in the subtree rooted at 7 is 3. And now that that's done, we can return back up to the 1, and the 7 says, hey, my number is 3. And the 1 says, okay, now I need to go down the right tree. So 9, you know how many nodes here? So 9 is going to calculate 2 and return 2 back up. And the 1 is going to say, okay, I get 3, I get 2, I add 1 on for myself, and that gives 6. And so on and so forth. So that's how we're going to calculate the number of nodes in a tree rooted at a particular tree or subtree rooted at a particular node. For getting the height, so this is similar, but instead of counting the number of nodes, we're counting the number of levels, right? We're counting the height. Now, this setup of this method is also something that we'll see a lot throughout these files that we're going to be looking at. So the public method is just get the height, right? Because you have some node and you want to know what the height of that node is. And the height that we're using assumes that a 1-level tree has a height of 1. So, this is the first level. If 6 was all on its own, that would have a height of 1. If we just had a tree of 7, 6, and 11, that would have a height of 2. Okay? So when we have a node, like let's say 4, we want to know the height of 4. Well, we're going to invoke get height on a node. So we don't need to send in any parameters, right? Because we're just saying, okay, you're saying the node is the invoking object, give me the height. But because we're going to implement this recursively, we need to have a node as a parameter. So we're just going to make a private method where we have a node that's the parameter, and we just send this current object, so that's just the current node we're looking at, we send that in as a parameter. So in the private method to get the height, we start with node is just the root node, and we say, well, as long as that's not null, my height's going to be 1 plus the max of whatever the height of my left and right child are. So, for example, 4 is going to say, okay, 4 isn't null, so my height is going to be 1 plus whichever subtree is bigger. The subtree rooted at 1, the height of that, or the height of the subtree rooted at 3. And 3 is going to say the same thing, for example. So 3 is going to say, okay, my height is 1 plus the maximum of whichever height is bigger, the subtree rooted at 2 or the subtree rooted at 12. And 2 is going to say, okay, I'm not null, so my height is 1 plus whichever height is bigger, the height of the left subtree or the height of the right subtree. The height of the left subtree, we get down to 5, and the node is not null, so we would actually invoke with the left and right subchildren, but those are null, so then we return back with just a 0 from each of the null children, and we'd say, okay, the height of 5 is 1. Now, 2, when we try to invoke on the right child, it's null, so that's just going to return a 0. So 2 is going to say, okay, my height is 1 plus the max of 1 and 0. The max of 1 and 0 is 1, so that's my height at node 2 is 1 plus 1, so 2. And now the 3 says, okay, well, my left tree has a height of 2. Let's look at my right tree. My right tree is a 12. I would invoke with the 2 children. Those would both return 0. So 12, the height is 1. So 3 is going to say the height of my left child is 2. The height of my right child tree is 1. I'm going to take the max of those 2, and I'm going to add on 1 for myself. So the height of 3 is 3. Okay, so that's how we get the height. Again, it's this idea of recursively calling a method, but not necessarily on the same node, right? So we're invoking get height on the current node, but we're going to recursively call it on the node's left child, and that node's left child, and that node's left child, and that node's right child, and so on and so forth. And the other common setup that we'll see here is this idea of creating a private helper method so that we can have a node as a parameter. Because in the public forward-facing method, we don't need a parameter, but internally to do the recursion, we do. Lastly, we have a copy method. So all that the copy method does is it just gives you a new binary node with the same data. So we just create a new node that has this data. So initially the left and the right subtrees are null. And then we check to see if they're null. And if the left or right subchild is null, we're just done. But if the left child is not null, then we set the left child to be a copy of that child, that node. Okay, so this is again recursively invoking this method on the left child and then doing the same on the right child. Okay, so we would just kind of go down that tree. If we wanted to create a copy, we'd say, okay, I'll create a new node that has the data of 4. And then my left node is not null, so I'm going to ask 1 to copy itself. And 1 would say, okay, I'm going to create a new node of 1, and my left node is not null, so I ask 7 to copy itself. Left node is not null, so I ask 6 to copy itself. Left and right node are 6, so I just return 6. And then 7, my copy of 7 would set 6 to be the left subchild. Same thing would happen where my copy of 7 would then set 11 to be the right subchild. And now 1 will set, because that recursion is done, 1 will set its left subchild to be 7, but of course 7 is the root of that new tree, a copy, right? So we're going to end up with a copy of the whole tree. So that is the code for a binary node. And of course, a binary node is the basic building block of all of the trees we're going to be talking about. So that's the walkthrough of binary node. Next up, we're going to walk through binary tree.